For decades, automotive safety standards like ISO 26262 operated under a strict binary. The goal was to prevent hardware degradation and eliminate software bugs. If the components didn't break, the car was safe. Modern autonomous driving systems face a paradox that breaks this model. A vehicle can execute its code perfectly, using flawless sensors, and still crash simply because environmental conditions overwhelm its capacity to perceive the road. Engineers classify this as performance insufficiency. The catastrophic failure originates not from a mechanical defect, but from the limits of the machine's ability to interpret a chaotic physical world. To address this specific blind spot, the industry developed ISO 21448, widely known as SOTIF, the safety of the intended functionality. SOTIF provides a rigorous engineering framework to identify unknown operational hazards and systematically bring them under control. Engineering for the physical world requires a focus on mapping and controlling external chaos. The baseline for safety has moved from the prevention of broken parts toward the management of environmental variables. Within the SOTIF standard, Chapter 8 serves as the precise execution phase. This is where identified risks are met with concrete physical and algorithmic countermeasures. Class 8.3.2 System Modification is an offensive strategy. A blue upward arrow shows technology expanding the vehicle's operational design domain. On the right, Clause 8.3.3 Functional Restriction is defensive. An orange downward arrow shows the system accepting physical limits, pulling boundaries inward to reduce authority. Every modern Level 3 and Level 4 autonomous architecture is built upon the tension between these two clauses. The conflict plays out across three distinct layers: the physical hardware, the algorithmic logic, and the interface. Autonomous reliability emerges from this dialectic. A vehicle needs mechanical ambition to push forward, balanced by programmed humility to know when to stop. At the physical layer, the most immediate threat is lens occlusion. Mud, snow, and road salt act as triggering conditions that corrupt data integrity long before it reaches the perception algorithm. To diagnose this occlusion, Clause 8.3.2 explicitly favors classical edge detection algorithms over modern deep learning. Neural networks can output unpredictable results when presented with unfamiliar types of dirt, but edge detection relies on deterministic physics. This simulation shows the Sobel operator mechanism in action. A 3x3 matrix kernel calculates horizontal and vertical pixel brightness gradients across the feed. Rather than guessing the object, it mathematically isolates areas losing sharpness, mapping a static zone that confirms physical occlusion. Once diagnosed, the system executes an offensive 8.3.2 hardware modification. It deploys active interventions, like Vallejo's centrifugal spinning lenses or piezoelectric air jets that blast away water while simultaneously cooling the high-resolution sensors. However, hardware alone cannot solve algorithmic hallucinations. Clause 8.3.3 must account for situations where a clean perception system confidently identifies a shadow as a solid lane marker. This generates a false positive driving command. If a lane-keeping assist system misreads the road and possesses absolute physical authority, it will violently steer the car into a barrier. This cross-section of a steering column illustrates the defensive restriction. Engineers hard-code a strict mechanical limit, capping the maximum automated steering torque at approximately 3.5 Newton-meters. This specific torque ceiling ensures that an adult driver can effortlessly overpower the machine. When the camera's confidence score drops, the system physically degrades its own steering authority to protect the driver. At the hardware layer, the vehicle forcefully clears its vision to fight the environment, while intentionally capping its mechanical muscles to mitigate its own errors. Moving deeper into the algorithmic layer, SOTIF addresses the risks of relying entirely on black box deep learning models. Convolutional neural networks are highly capable, but their vulnerability to data bias makes them prone to unpredictable edge case failures. To counter this, Clause 8.3.2 dictates a hybrid architecture. Engineers pair these advanced neural networks with a much older tool, the histogram of oriented gradients, or HOG. HOG calculates simple geometric shapes. By running it in parallel with deep learning, it provides an explainable, shape-based cross-check for high-risk safety protocols, like emergency braking, verifying the primary network's decisions. This 3D topographical map displays another 8.3.2 algorithmic modification, predictive environmental modeling. The system combines GPS coordinates, time data, and astronomical ephemeris charts to calculate the exact moment a sun glare vector will intersect the camera's trajectory. Armed with this prediction, the vehicle adjusts its camera exposure or shifts its data reliance to radar and LiDAR before the sunlight ever hits the lens. Yet predictive modeling has limits. Clause 8.3.3 steps in for scenarios that cannot be outcomputed. Torrential rain scatters LiDAR lasers and distorts camera pixels simultaneously, rendering offensive algorithms useless. The required response is dynamic ODD reduction. When sensor data degrades past a mathematical threshold, the system enforces the ultimate restriction. Fleet operators execute this in real time. When specific precipitation or visibility metrics are crossed, robotaxi services actively ground their fleets or route active vehicles immediately to safe harbor. The software must aggressively predict failure and cross-examine its logic. But it must also retain the architectural discipline to shut the service down when nature wins. The SOTIF framework extends beyond the internal logic of the vehicle. It governs the psychological interaction between the autonomous system and external actors, like pedestrians and law enforcement. Clause 8.3.2 requires conspicuousness to manage this interface. Mercedes-Benz achieves this by deploying turquoise marker lights. This distinct color explicitly broadcasts to the surrounding traffic that the vehicle is in an active Level 3 eyes-off state, reducing human unpredictability. To prevent pedestrians from misinterpreting a silent electric vehicle, engineers deploy acoustic vehicle alerting systems, or AVAS, as an auditory interface. These acoustic signatures are heavily engineered. Collaborating with composers, manufacturers build soundscapes that intuitively communicate the vehicle's mass and acceleration to anyone nearby. But external communication is only useful while the system is functional. When boundaries are breached and the system can no longer guarantee safety, Clause 8.3.3 mandates the handover protocol. This logic flowchart maps the strict UN R157 regulation for automated lane keeping systems. It requires a transition demand, a strict 10-second countdown. This guarantees the human driver has the biological time required to disengage from other tasks and regain situational awareness. If the human fails to respond and the timer expires, the protocol triggers the minimum risk maneuver, or MRM. The vehicle autonomously halts in its lane or moves to the shoulder, reducing its kinetic energy to absolute zero. The system uses lights and sounds to broadcast its competence to the world, but it relies on an uncompromising timed kill switch to shut down entirely if the human link fails. This matrix synthesizes the opposing strategies. On the left, we map the aggressive expansion measures of Clause 8.3.2, active sensor cleaning, hybrid algorithms, and turquoise lighting. On the right, we map the rigid restrictions of Clause 8.3.3, physical torque limits, dynamic ODD reductions, and the MRM protocol. Executing only the left side creates extreme danger. Pushing performance expansion without limits results in unverifiable code complexity and massive SOTF risks on public roads. Relying solely on the right side creates commercial failure. An overloaded system refuses to drive, destroying product utility. True compliance requires balancing these opposing forces. The mathematical equilibrium between expanding capability and restricting authority establishes the SOTF safety bounds. Advanced autonomous engineering generates safety by expanding system capability while precisely orchestrating its own mechanical and logical limitations.